Okay, copy C, Unit 3, Day 7, Office Hours, page 535, 119 odd. Should check your odds in the back a bit. First, several problems are just review of what we were doing the day before. So, giving you the parametric equations, and asking you to sketch them, find the Cartesian equation. Now, it's the same thing as saying that T is of 0, 3. So let's get the Cartesian equation first. Price solve for T. 2T equals x minus 3 divided by 2. T equals x minus 3 over 2. I'm going to plug that in to the other equation. Distribute 2x minus 6, 2x minus 9. So it's a line. It's going to be a line segment because of the restrictions on time. So draw a sketch. One, two, three, 4, 5, 6, 7, 8, 9. So up 2 over 1, 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 lightly. So we make a table. 0, 3. That's going to be 3, negative 3. So this is your initial point. And 3, you plug 3 and you get 9. 12 by 3, 9, 9. Yeah, I guess I should have made this graph bigger in the vertical direction. Anyways, well, it's going to be somewhere up here. Did the math wrong in my head. So 9, 9, terminal point. So I'm pretty sure this is the direction. You can plug another point in if you want. 1 would be 5, 1. It's right around there. So it's a line segment. Okay. So 3, negative 3. 9, 9. All right, 3. Now it does say find an equation that relates x and y directly. Okay, so which define y as a function of x. Sketch curve, we're going to identify this. Okay, so number 3 has some trig in it. So you're going to need those Pythagorean identities, trig identities. So you should be able to run down from memory at least once. Basic one, sine squared plus cosine squared equals 1. Divide everything with sine. Cosine over sine is cotangent. 1 over sine is cosecant. Divide everything by cosine. Sine over cosine is tangent. Cosine over cosine is 1. 1 over cosine is secant. Great, so we're going to use those. So we're going to use this one on this problem. So tangent is just x, so that's going to be x squared plus 1 equals y squared. Now, if we get the y squared on the same side over here, move this over here, that's hyperbola, but we're going to want to divide everything by -1 to get that as a positive 1. So now we could use that. We could also solve it for y in terms of x, which kind of sort of seems to say that. So if you undo that, that'd be plus or minus the square root of x squared plus 1. It might end up just being the plus or the minus, depending on the portion of the curve that we graph. We could sketch the graph. So up 1, draw a box, connect the diagonals, connect the corners, the diagonals. Those are going to be slant asymptotes. And then because y is positive, it's going to be up and down, top and bottom ones. Okay, we're going to make a table. We're going to go 0 to pi over 4. So we plug 0 in here. Tangent is sine over cosine. Sine of 0 is 0, cosine of 0 is 1, 0, 1 is 0. Secant is going to be 1 over cosine. Cosine of 0 is 1, so that's going to be 1. So 0, 1 is the initial point. And this is a hyperbola. Pi over 4, that's going to be 1. Sine of pi over 4, cosine of 4, root 2 over 2, root 2 over 2 is 1. 1 over root 2 over 2, which is the same as 1 over root 2. That's going to be root 2, which is about, I don't know, 1.3 between square root of 1 and square root of 4, between 1 and 2, closer to 1 than 4, maybe 1.3. It should make sense on this graph, hopefully. Yeah, it looks about right, 1. That's the terminal point. So it's just going to be this portion of the curve right here going from that to that. So we could just go with the positive here. And there you go. Okay. Number 5. Now this one has some unique trig challenges to it. So we're gonna use. Now here's the problem. X squared could be sine squared, but y squared is going to be cosine squared 2t, and that's not quite. We can't just plug that in. So what we have to use is we have to use double angle identity from trig. It says if you have cosine of double of an angle, then you can break it up. The cosine t squared minus sine t squared. And then that presents some more new challenges. We want, and that's cosine 2t, by the way. So then it would get squared. I guess we could just go, let's just take a break and just focus on this. I'm trying to rewrite this. So what we could do is, okay. Now, what we could do is we could plug this into sine squared. So it's kind of like substitution, but we need to get rid of the cosine squared. Cosine squared is 1 minus sine squared, using that same Pythagorean identity, right? And so this is the same thing as 1 minus 2 sine squared. So then another way of writing cosine 2t is that it is 1 minus 2x squared. And we know that this equals y, right? So I kind of took a break from that. So then now let's see, sine squared, that's x squared. Okay, there you go. I mean, that's the equation, y equals 1 minus 2x squared. So this was a little challenging. It's parabola. So we draw a sketch of it. It's going to be an upside down parabola. That's been shifted up 1. So up 1. So it kind of looks like this. And let's make a little table and find initial and terminal points. So it's going to be 0 to 2 pi. Plug 0 and sine of 0 is 0. Cosine of 0 is 1. So that's the initial point, 0, 1. Okay. So 2 pi, sine 2 pi is 0. Cosine of 4 pi is 1. So this is the initial point and the terminal point. This is interesting. What's going to happen here? So if we plug, say, pi in, what happens? We get 0, 1 also. So even at pi, it's back there. How about pi over 2? That would be 1 cosine of pi would be 1 negative 1, 1 negative 1. And then say 3 pi over 2 would be negative 1. That'd be cosine 3 pi, negative 1, negative 1. So that would be over here. I mean, we could try and plug in a couple other values like pi over 3 would be right here, just to get it better. So pi over 3, sine of pi over 3 is root 2 over 2, and cosine of 2 pi over 3 is negative 1/2. And root 2 over 2 is the same as 1 root 2. I don't know. It's going to be less than 1. It's going to be like a fraction. So that's like right here. So it goes from here to here to here. And then I'm assuming it just keeps going, right? And then as we get closer to pi, if we said, say, 2 pi over 3, that'd be root 2 over 2, and then positive, no, that'd be 4 pi over 3. That'd be, that would be negative also. So I think maybe what's happening, it's the whole graph. It's going out this way and coming back in this way. I don't know. It's kind of crazy. So whatever. It's definitely a challenge. Kind of interesting. We've done problems before without trig, and so this one had trig. So that kind of made it weird. Now the next problems, so those first few were just review. The next problems are saying find dy dx and find the second derivative of y with respect to x in terms of t. So remember that dy dx equals dy dt over dx dt, and then also the second derivative of y with respect to x. We talked about how to do this is the derivative of dy dx with respect to t divided by dx dt, and it all comes from some like implicit differentiation idea. So on number 7, you have x equals 4 sine t, y equals 2 cosine t. So dx dt is 4 cosine t, and dy dt is negative 2 sine t. So dy dx is, now make sure you put dy dt on the top. Now we could simplify this and say that this is negative 1/2 tangent t, right? And then the second derivative, so that's part A. Part B is the second derivative. So we're going to take the derivative of dy dx first, and that's going to be negative 1/2 secant squared, and then we're going to divide it by dx dt, which we found earlier was 4 cosine t. Now remember, secant is 1 over cosine, right? So that could be another secant. We could write that the second derivative is negative 1/8 secant cubed. So that's number 7. Number 9. That's x. This is y. Probably want to think of those as powers. So dx dt is negative 1/2 t plus 1 to the negative 1/2. Write it as negative 1 over 2 square root of t plus 1. Dy dt is going to be 1/2 3t negative 1/2 times 3 chain rule. It's going to be 3 over 2 square root of 3t. So dy dx is going to be dy dt over dx dt. Clean this up. Multiply by the reciprocal, so we get so dy dx equals 2's cancel, negative 3 square root of t plus 1 over 3t. Or some version of that. I mean, we could rationalize the denominator, and this 3 would cancel with those 3's. You'd have negative 3t squared plus 3t all over t. I guess that's another version of the answer. So something like that, some version of that. Okay. Then second derivative. Take the derivative of dy dx. That's going to be messy. Unless we clean it up. I don't know. This one's going to be a little fun. We do this one. So t plus 1 over 3t to negative 1/2 times derivative of what's inside. That's going to be chain rule, low, d high minus high, d low, all over low squared. Then we're going to divide by dx dt. This is a mess. Negative 1 over 2 square root of t plus 1. Yeah, I don't know. It's pretty bad. We could try and clean this up, but I mean, this is negative 3 square root of 3t over t plus 1. And then this is going to end up multiplying by the reciprocal. So that would get rid of the t plus 1s and the square roots. And then this is going to be 3t minus 3t minus 3. So that just becomes minus 3, or 9t squared. The 3's and the negatives become positive in the 9. So I think we're to the negative 2 square root of 3t over t squared. I guess it got a lot better than I thought it could, but I don't know if I'm still missing something. My answer looks like I shouldn't have the 2 there. Should the 2 have got away? I don't see where the 2 should have gone away, but oh, yeah, sorry. When I take the derivative, it's supposed to be times the first exponent, so 1/2 goes in front. So there is an extra 2. The 2's cancel, so there it shouldn't be a 2 there. Okay, that was challenging. We'll do a few more of those. So 11. So A, we're gonna, let's see. So we're gonna do dx dt, dy dt. So dy dx equals dy dt over dx dt. This one's making up for the last one. This one's turning out to be a little easier. In part B, we got to take the derivative of that with respect to t. So it's going to chain rule, low d high minus high d low all over low squared. So that's going to be 12t squared minus 18t minus 6t squared. Probably leave the bottom the way it is. So that's going to be 6t squared minus 18t. I don't know. It might be worth it to factor this. Looks like we might be able to simplify it a little bit. So if we took a 6t out, I would leave a t minus 3. No, that doesn't really do anything. I thought it might, but it doesn't. Okay. So I think we'll just go with that. Second derivative. 6t squared minus 18t. I mean, you can factor it. It just doesn't help. So in retrospect, I just wouldn't have done it, but the bottom line would just be factored. 13. So part A, dx dt. Oh shoot, I forgot on this one. Never divided by dx dt. Which is 2t minus 3. So that's where the cube comes from. There's an extra 2t minus 3 in the bottom. Okay. Dx dt equals tangent. Derivative tangent is secant squared. Dy dt equals secant tan. Dy dx is going to be secant tan over secant squared. Tangent is sine over cosine, and secant is 1 over cosine. So in cosine, so dy dx ends up just being sine t. That's nice. And then we need to take the derivative of it with respect to x. And we need to divide by dx dt, which was secant squared. Now secant is 1 over cosine, right? So that's going to get flipped to the top, and the second derivative is going to be cosine cubed. Nice. That one was a lot better. And got one more. Getting some different derivative practice in here. Let's see, 15 is now when we take derivatives of natural log, a lot of times we use log rules to help it out. So we could break this up. I mean, we could do even more than that, but that one right there by itself is going to be helpful, I think. So it's going to be 1 over 2t times derivative 2 of what's inside. So it's going to be 1 over t. Dy dt is going to be 4 times 1 over 3t times derivative of what's inside. So you get 4 over t. So dy dx is going to be 4 over t divided by 1 over t. Dy dx is going to be 4. Nice. So then for part B, we're going to take the derivative of that with respect to t, which is 0, and divided by dx dt, which is 1 over t, but 0 divided by anything is 0. So the second derivative is 0 there all the time. Okay. And then 17, 19, get to do a little extreme value theorem stuff in there. It says sketch the curve, indicate the direction, identify the request point, justify that you have found the request point by analyzing an appropriate derivative. So 17 is x equals t plus 1, y equals t squared plus t, looking at negative 2 to positive 2 and t, and we're looking for the lowest point, which means we're looking for min y, right? So let's get the equation, get the sketch first, which is really just help us feel, I guess more confident about our answer. So I'm going to solve for t. T equals x minus 1. Plug that into the other equation wherever I see t. So y equals x minus 1 squared plus x minus 1. So y equals x squared minus 2x plus 1 plus x minus 1. So y equals x squared minus x. That's your equation. It's a parabola. And There's different tricks we can do. We could factor it to find its roots, its x-intercepts, and the asymptote would be exactly halfway between those. So this is going to be a parabola. We're going to, plug in some values. -2 to 2. So we know what portion of the graph it is. Maybe 0. So -2 would be -1, 6. 2 would be 3, 6. No, not 3, 6. So this one would be 2. -1, 2. Plug 0 in just for another point. Be 1, 0. So let's sketch this parabola. 0, 0, and 1, 0 are its x-intercepts. -1, 2 is right here, 3, 6 is here. So this is what the parabola looks like. And let's see, -1, 2, this is the initial point. And 3, 6 is the terminal point. So it's going to be everything in between. And the graph is moving this direction. So we're kind of doing all the stuff we've been doing. Okay. Now you look for the lowest point, which is clearly right here. It's the vertex of the parabola, but we're going to use calculus to support our answer, to justify it. So if you want the lowest point, that means we're looking for min y, which means we need the critical points from y. dy dx equals 0, which is when no. So that's going to be when dy dt equals 0. It's kind of normal EVT, right? The thing you're trying to minimize and maximize, say equals 0, undefined. Find critical points. So dy dt equals 2t plus 1, so equals 0 undefined. And t equals -1/2. See, I think I made a mistake somewhere. -1/2. Okay. I'm trying to think. This doesn't necessarily match my graph. Huh. Because it looks like it should be like +1/2, right? So that doesn't quite make sense. My work. Oh, yeah, never mind. This is the time. That's the critical point. Okay. Getting confused. Mixing t's with x's and y's. This x equals 1/2. So let's keep going. We got endpoints up here. -2 to 2. We make a table. And we go -2 to, oh, we already kind of made the table. So we could just add it to that table. -1/2. X equals, if you plug -1/2 in for time, you get +1/2, and for y, you get 1/4 minus 1/2 is -1/4. So this right here is your lowest point, your smallest y value. So so the lowest point is 1/2 negative 1/4 at time t equals negative 1/2 by extreme value theorem. Checking endpoints and critical points. Okay. 19. Last one. X, y, time, 0 to pi. Looking for the rightmost point. Rightmost point, which is max x. Right? It's all about x. Right, left, it's all about x. So let's just try and get our graph first. Sine squared, that's going to be x over 2 squared plus cosine squared is going to be y squared equals 1. X squared over 4 plus y squared over 1 equals 1. This is an ellipse. So we could start sketching it. It's going to be bigger left and right. Draw a box to fit the ellipse in. Okay, make a table that we could probably even use for our extreme value theorem later. But for now, we're plugging in to find the endpoints, which are part of the extreme value theorem. If we plug 0 in, that's going to be 0, 1. So 0, 1 is the initial point. Pi, it's going to be 0, negative 1. So 0, negative 1, the terminal point. Probably at least need to figure out what portion of this graph it is. If I plug pi over 2 in, I get 2, 0. So it's going over here on the right side. So I'm going to darken in the graph. The direction is this way. And we're looking for the rightmost point, which is clearly here. It's 2, 0. But we're going to show some calculus. And we already have a lot of work. So we got to find, now one, the rightmost or leftmost point is going to happen when the vertical tangent, or when the tangent is undefined. Now remember, dy dx equals dy dt over dx dt. And the reason you're going to get undefined is because dx dt equals 0, which also makes sense because if you're at the furthest right or furthest left, even like relatively, then there can't be any more motion left or right at that point. Otherwise, you could get further left or further right immediately. So dx dt equals 2 cosine t. And we're going to say equals 0 undefined. And so cosine equals 0. And so t equals pi over 2 plus pi k. So t equals pi over 2. That's the only critical point. So we're going to, hey, we already calculated that just by accident. That's a critical point. We already have it. So this right here is the rightmost x value. It's the x's that we care about. So we found it. So we're going to say the rightmost point is 2, 0 at time t equals pi over 2 by extreme value theorem. checking endpoints and critical points. There you go. Makes sense with the graph. We got the calculus, we got the work. Hopefully you guys are getting really good at all this parametric stuff. We'll start doing more stuff with them.